Yesterday. It will be, let's share the speakers. Next one. So it will be presented by Dr. Aamir Shafi. He's a research scientist where he's involved in the high performance big data project. I referred to yesterday as HiBD. He was a Fulbright visiting scholar at MIT where he worked on the award-winning Silk technology. Then he received his PhD in computer science from the University of Portsmouth, UK in 2006. His current research interests include architecting robust libraries and tools for big data computation with emphasis on both machine learning and deep learning applications. He has also co-designed and co-developed a Java-based MPI-like library called MPG Express. So today, in this session, he will be talking about high performance and scalable support for big data stack with MPI. That is the MPI for Spark I introduced yesterday. So Aamir, you are ready?
Yes. Are you able to hear me, Dr. Panda?
Yes, we can hear you.
Okay.
We can see your slides also. Go ahead.
Sure. Thank you. So thanks everybody for sticking around. Last talk of MUG 2023. So I will give updates on our big data stacks that we have been developing over the last couple of years. And this is a joint work with Kenan and Jinghan, who are graduate students in our lab. So here is the presentation outline. I'll just say a few words about big data analytics, and then I'll go into give some overview about MPI for Spark and MPI for Dask, and I will towards the end I'll present some of the evaluation numbers. So big data analytics is obviously an important workload today. So our point of view is that we have a lot of lessons learned and technologies developed in high performance computing area that can be utilized in the field of big data, and that's essentially where we are coming from. So we feel that both the fields, it's possible to converge them to meet the large scale data processing challenges and requirement of the big data application. So if you're writing a big data application today, or let's say you have a big data set and you want to do some filtering or pre-processing, you have basically two popular options available to you. So the first one is the Dask ecosystem, which is Python centric, and then the second one is Spark, which was developed in Java, Scala, but now obviously it supports Python as well. And this field is also called data science in some literature. So next up, I'll just give some details about the MPI for Spark software. So here is the architecture diagram of Apache Spark, and basically our main motivation has been that we would like to utilize the communication functionality provided by MWPitch in the Apache Spark ecosystem. So Apache Spark, if you look at this block diagram, makes use of this software called Netty, and Netty is basically a Java new IO client server framework for event-based networking applications, and this typically is implemented on top of Java sockets that makes use of TCP, and obviously Java sockets and TCP/IP stack has its own overheads. So, and our idea here has been that instead of using Java sockets, is it possible to utilize, let's say, an MPI library, because there is point-to-point communication going on during the shuffle phase. So is it possible to utilize MPI-based communication in there? So obviously the first thing that we had to develop in this context was come up with Java bindings for MPI library. So in this context, I would just connect back with the ABI compatibility that Jeff presented yesterday. So we actually had faced that issue because OpenMPI in the production release, they have Java bindings available, but it's not possible for us to just use that software on top of MWPitch 2 because of ABI compatibility. So hence we had to implement our own Java bindings, and we do that through the Java native interface. And this MOPH2J, our MOPH bindings are also available as software, separate software. So our main motivation for developing Java bindings was MPI for Spark project, because we had to develop that particular software layer in order to be able to use MPI in the Apache Spark software. So what MPI for Spark or this work has enabled is that it's now possible to utilize Spark on different high performance interconnects. So previously we have, from our own lab, we have an optimized stack called RDMA Spark, which makes use of IBverbs library, but that only works on top of InfiniBand or Rocky. But on the other case, MPI for Spark, which makes use of MOPH2, works on top of a variety of interconnects. Essentially, wherever MOPH2 works, we MPI for Spark, we are able to support MPI for Spark over there as well. So one of the challenges that we had to tackle here was that in the startup of Spark-based execution, there is a lot of process forking. So basically, we start worker processes, and these worker processes then in turn start these so-called executor processes. So there is forking, basically starting these new processes or forking going on that we had to tackle in an MPI-based application now. So we made use of the dynamic process management feature of MPI in order to essentially do that. And this is not a very widely used feature of MPI, but here is a real world use case where our work, MPI for Spark would not be possible if MPI doesn't support the DPM feature. So this is an upcoming release of MPI for Spark. We should be making this release in the coming days. And what this basically does is that we are adding support for the Yarn cluster manager. So previously, in our previous 0.1 version, we were only supporting the standalone cluster configuration of Spark, but now with this new release, we will support the Yarn cluster manager as well. So with this now, I'll move to MPI for Dask, which is our optimized stack for Dask. So Dask is a popular task-based distributed computing framework. It already has two communication backends, TCP, and it has one based on UCX as well. So, and our idea here is similar. We want to inject MOPH2 in the software stack in order to utilize high performance point-to-point communication implemented by or provided by MOPH. And since Dask is Python-based stack, so in this case, MPI for Py, which is a very mature Python wrappers, or bindings for the MPI library, is already available. So we simply made use of that. So here is the Dask distributed model. So essentially, the scheduler is the central entity here. And we could start worker processes, they connect back to the scheduler, and this together, the scheduler and the workers, they form what is called a Dask cluster. And then when the user wants to, let's say, submit their job, it's possible to do that using client. Client connects to the scheduler, and then the user can submit jobs for execution through the client to the Dask cluster. And here is the software stack of MPI for Dask, and I would just focus on this distributed layer. So this is the layer of Dask that supports parallel and distributed execution of Dask processes. It provides the notion of scheduler, workers, and clients. There is this TCP device, and then the UCX device that makes use of UCX PY Python wrappers. And in our case, we basically added these yellow boxes. We added what is called MPI for Dask, and then this works on top of MOPH2, and this basically happens through the Python library, which is MPI for Py here. And here is basically, We made use of this software called Dask MPI. So this is another package which is already provided by Dask. What this does is that it lets you bootstrap execution of a Dask job using MPI launcher. So this basically saved a lot of work. Otherwise we had to do this work if we had to bootstrap, let's say, scheduler, workers, and clients through MPI. We did this in the MPI for Spark project, but this effort was saved by essentially the Dask MPI project for us. So we were simply able to use this package and start the execution of Dask programs using MPI launches through the Dask MPI project. So this is the last release that was made in February of 2023. And in this case, we upgraded the version of Dask distributed, and we also added new benchmarks and also tested this software on some new hardware. So I will now move on and present some of the performance evaluation numbers. So I'll start with MPI for Spark. So here are some weak scaling numbers, and this is with our own OSU high BD benchmarks. These are called OHB, and the two tests that we are seeing here are group by test and sort by test. And if we, let's say, focus on the left-hand side, we basically see, the execution using the TCP, which is the vanilla Spark, and then we have execution using for RDMA Spark, and then we have MPI for Spark. And then essentially we have numbers for 8 workers, which means approximately 500 cores, 16 workers, and 32 workers, which basically means that approximately 1800 workers. And as we are increasing the number of workers, since these are weak scaling results, so we are also increasing the overall problem size. And in this case, you can see that we are able to gain significant speedups compared to the vanilla Spark, as well as speedups compared to RDMA Spark. We also see similar trends on for this other sort by test. Here the gains are 3.8x and 1.5x. And these numbers are using the standalone cluster manager in the Spark software. So these are some new numbers, and this release is not yet available publicly, but for this particular execution, we are basically using the Yarn cluster manager as a resource manager. Again, similar results, weak scaling, the group by test, and we are basically seeing better performance, similar trends essentially compared to as we had seen for the previous resource manager. We also did some performance evaluations using application level benchmarks, so coming from Intel High Bench workloads. So compared to RDMA Spark, we see for this particular, some a variety of machine learning workloads, we see around 1.4x on average speed up. And we also see similar speed, trends for other micro graph workloads and micro machine learning workloads. And it's important to say here that, note here is that the first two graphs here are on the TAC Frontera system, which is InfiniBand system. So which basically means that we were able to run RDMA Spark, but the last system is the TAC Stampede 2 system, which has Omnipath network. So in this case, software like RDMA Spark won't even run. But since we are relying on Apache 2 and that works on Omnipath, so we are able to run MPI for Spark on this particular system. So moving on to MPI for Dask results. So these are some numbers on the Cambridge Wilkes 3 system, which is equipped with NVIDIA A100 GPUs. And in this case, you can see on the x-axis, we have number of Dask workers going from 2 to 32 GPUs. And on y-axis, we have the execution time. The lower is better. And we are comparing again against TCP, the UCX device, and then this red is our own MPI-based, the Dask ecosystem. And we are seeing significant speedups even compared to UCX as well. So for example, on average, this is around 5x the speedup. So this is execution time. We also see similar trends for aggregated throughput. The gains are more, pronounced in this particular case. This is another, PUPI GEM benchmark. Again, similar trends, approximately 4x faster than UCX. And then we also see some performance improvements on, I mean, not only GPU systems, but we also see performance benefits on the CPU systems as well, because the Dask ecosystem, it can execute on the CPUs as well as the GPU ecosystem. So, we see in this particular case some, not that pronounced gains, but still, there are, on average, we have around 1.2x speed ups. And this is, these are for the latest release, which is available on the website, which is the 0.3 release of MPI for Dask. So with this, so these are some of the related publications. You are welcome to, view them. And, I'll just conclude my talk that, Apache Spark and Dask are two popular big data frameworks. And, there's existing support and, requirement for running these workloads on HPC systems. And obviously, the communication stack is not that optimized. And this work is an effort in that direction that, is it possible to utilize MOPH2 to optimize Dask and Spark ecosystem? And apparently, we have had some early successes, and we will build on these, in the future and report back in the coming versions of MUG. So with this, I conclude my talk. Thanks a lot for sticking around and, for your attention.
Any quick questions for Aamir? From anybody here? Okay. There is an online question. Yeah, go ahead, read it. Yeah.
There's
Aamir?
one online.
Might it be possible to standardize the MPI Java bindings? Yes, that's a long-standing issue. So, before we did this work, I was involved in a separate Java MPI library called MPJ Express. And then Open MPI, had their own Java bindings. So in this work, we have actually tried our best to stick to the API that is used by Open MPI. So, from the API viewpoint, we have a lot of similarities with Open MPI, and obviously, I think we will need to form a body that will take care of that. And I think this is an important thing. If there are interest in using Java and HPC applications, then I feel, this obviously needs to happen. Yes.
Any other questions from anybody? Okay. So if not, Aamir, thanks a lot again. Okay.
Thank you.
Yeah, so I think with this, we'll officially close. I mean, we started on Monday morning. I mean, it has been 3 days of intense presentations, discussions and all. I hope all of you liked it. We have been collecting the slides behind the scene, and I think in a few days, we'll be posting them all to the website, the MUG website, the slides, the videos, as the speakers give us permission. Okay, so that is happening behind the scene. And as you saw, there's a lot of work going on, and a lot of things are in the pipeline. And if you want to use any of the future features, just keep an eye on our release list, mailing list, and then you will be seeing those releases coming out. And also we have a lot of collaborations being expressed by a lot of people during the last 3 days. We'll be pursuing those one after another. And with that, I'd like to wish all of you a safe travel. And then we'll be very happy to meet with you again at all different places. I think the next big event is the supercomputing. And I'm sure many of the people here will be there. We'll have an OSU booth there. And we look forward to interacting with all of you. Okay. So thanks a lot again. Okay.